Thank you, Lorena. Yeah, we made it to the last presentation, so congratulations to you. I've used a little bit of the template, adding the logos mostly as a reminder for myself to acknowledge the contribution from the partners to these tasks. At Vito, we focus on the development of the technologies to valorize this aggregate washing residue from Velde in Norway. Velde contributed with the execution of one of the pilots. We had 3 pilots involved here. We did 3 different technologies for valorizing this residue. And then the Danish Technical Institute contributed with the development of the end-of-waste criteria. So why is this valorization important? Mostly because of the volume that is processed at the production plant of Velde. They process excavated material to produce secondary aggregates mostly. But in this production, the washing process to remove the fines, which are very detrimental for the properties of the aggregates, are left as a sludge that accounts for 20 to 30% of the weight of the processed material. So that's a significant amount of residue at the rate of approximately 45,000 tons per month. And that's why a valorization path for this material is very necessary. So we work on the technical validation, mostly at Vito, but as I said, also the end-of-waste criteria to facilitate the implementation of these technologies and the demonstration with pilot production. We analyze the material and we determine that it contains approximately 25 to 30% of clay material. And this is quite significant data because it explains a little bit the value it can have for producing construction materials. I will go over the technologies in a minute. We also determine with different sampling campaigns the wide particle size distribution that we have in this material, also requiring some mechanical treatment for the applications. So going directly into the solutions, the first one we tested and validated was the use as a filler. And this is a material that is very much needed for concrete production. We developed 2 types of concretes, one that is plastic, more conventional concrete, but with a low content of filler in it. And then we also went into this bigger challenge of developing self-compacting concrete with this filler. Self-compacting concrete can contain up to 160 kilograms per cubic meter of concrete of this filler. And we developed a recipe that is robust enough for incorporating this filler. We had to go a bit higher in the water content, which is not good for the cost of the concrete. Also in the content of some admixtures like superplasticizers. The content of clay in the material was increasing this demand. So from the point of view of cost, that's not so convenient, but at the same time, the clays were providing more cohesion to the mix. And for self-compacting concrete, the resistance to segregation is very important. So in this sense, we could come with a solution that is more robust than conventional self-compacting concrete. We validated the mechanical and durability performance, so the concrete was in accordance with European standard EN 206, which was also a bit demanding because we are talking about application in a site like a Norwegian site with some requirements for free thaw there that makes durability concerns a bit higher than, for example, in the south of Europe. But we succeeded. Main conclusion for this is that to improve the competitiveness of this filler, some additional methods to try to reduce the clay content would be convenient. So we would have a material performing more similarly to other competitors in the market. With these concrete recipes, we went to Velde, and they produce these Lego blocks that you see here in the picture that have been exposed for more than a year at the moment. And they show no signs of any different performance than the concrete recipes that they are normally using. So this is a successful case that we could prove the filler can be used from a technical point of view in these concrete mixes without any impact on performance. Of course, the business case needs to be developed a bit further, exploring potential interest of clients in the Norwegian market. The second technology that we implemented was the production of supplementary cementitious material with this sludge waste. And this material is produced by calcination. We improved the composition of the raw meal by adding some small quantities of mineral additives to improve a little bit the reactivity. It's important to say that the supplementary cementitious material is valuable for the carbonization of the cement and concrete industry because you reduce the demand of clinker, which is a very carbon-intensive material. So by replacing 20 to 40% of the clinker that is normally used in cement, we can reduce the carbon footprint of the final product. So we reach reactivity levels of approximately 150 joules per gram. Probably that says nothing to you, but it's comparable to a siliceous fly ash, which is a supplementary cementitious material that is very present in the European market. So we can match the performance of a competitor that is very much used already all over Europe. Again, the content of clays was somehow limiting the performance of the material. In this case, because it was too low, we would like to have a higher content of clay in the material so we could reach even higher reactivity than 150 joules per gram. So there's still some possibility of continuing the research by concentrating these clays. And if we combine it with the previous technology, when we can have a separation technology, so we can have a sludge that is low in clay content for it to be used as a filler, and a sludge that is high in clay content for it to be used as supplementary cementitious material, then we will have a much better case for implementation and from the point of view of economy. One of the advantages that we noted for this specific material when we tested the performance in terms of durability was the increased chloride binding capacity. And this is an additional benefit when you are executing concrete in the marine environment, because chloride coming from the sea is detrimental for the reinforcement, the steel that is embedded in the concrete. So we want to avoid that this chloride is penetrating the concrete. And this particular material performed better than most of the competitors already in the market. And that was not a big surprise, but a bit of something nice we could add to the story. So for this material, we also have a pilot plan with this new baby that we have at Vito, a flash calciner. It's a bit of a naughty baby because, it's giving us a bit of issues at the moment. But we plan to execute this pilot and produce 1 ton of this material before the end of the Rotate project. So at the moment it's constructed and it's being commissioned, so we still need to do some tryouts before we can process the material at Rotate. The advantage of this flash calciner compared to the rotary kilns that are normally used for producing these materials is that in terms of thermal efficiency, you need less residence time of the material in the calciner, and also less fuel to reach the temperatures needed. And the third technology that we applied in this valorization strategy was the production of lightweight aggregate. And again, this is produced via calcination. First, some granulation of the particles, and then the calcination for sintering the material and producing these lightweight aggregates, which are normally expanded clay. That's the most common product in the market. But instead of using natural clays that are a primary resource, we were using this slash residue as a secondary material, so increasing much more the circularity of this production. Again, we had to correct a little bit the chemistry and mineralogy of this original sludge by adding some mineral additives, 10 to 20%. But we succeeded in the design of these particles that needs to be very porous internally. So you need to have a good microstructure that connects all the particles, but at the same time you need to have these bubbles embedded in the material. Here you can see a correlation between the density and the water absorption, which is a proxy for the porosity of the material. For this material, we are able to incorporate it up to 1,000 kilograms per cubic meter of screed. Screeds are a material that are normally not having structural purpose, so you don't have many concerns about strength, but it's mostly for example, thermal conductivity, that you would like a very porous material. So with this technology, we are able to replace a very impactful material such as expanded clay by using a secondary material. So with these recipes, we went to Poland. So with the subcontractor, we produced 1 ton of these sludge-based lightweight aggregates. Here you can see some pictures how we went from the small rotary kiln that we have in our lab to this big rotary kiln that we use in Poland, and there you have some pictures of the calcination ongoing there. At the moment, we are busy with testing the performance of these lightweight aggregates in screed mixes that we are producing at the moment at Vito. So this is a bit the end of the story. In terms of impact and benefit, with our results, we supported the transition to circular and resource-efficient economy in Europe. We validated scalable solutions for this sludge, and for the case of Velde, this translates into up to 45,000 tons per month of sludge material being valorized. We contributed to reduce the environmental and economic burdens associated with the management of this waste, because at the moment this comes with a cost for Velde, especially for the sludges that are contaminated, that need special processing and landfilling. And this comes with an estimated cost of 385,000 euros per month for Velde that could be eliminated by reusing the material. And we proved with the collaboration with DTI that the material can comply with the end of waste requirements for these applications. The technologies can also enhance the resilience by using local materials and reducing the reliance on external sources. So we can produce up to 30,000 tons of material per month by using these construction materials, by using these sludges. And finally, in terms of climate neutrality and zero waste ambition, we can reach 95 to 100% of material recovery for the whole volume that Velde is processing, that at the moment is at the ratio of 70 to 80% of recovery rate. So with this, we consider that we have fulfilled our goals at the beginning of the project. So that's all from my side. Thank you.